All right, so we're going to pick up where we left off from the lab and look at the relationship between force and position for a spring, and then leading us to a more important, the energy that gets stored in the spring. Okay, so we're going to develop the two equations that we already did in the lab with an example. And so look over this carefully, come in with questions and anything that's confusing to you. So we started with the spring. We put more and more force on it, and it stretches, and we find that the force and the position, or how much it stretches, are proportional to one another. Okay, so force changes with distance. Now this is very different than gravity, where force doesn't change with distance. It's pretty much the same, at least when you're near the surface of the Earth. So this is a little bit unusual. So when we do the work and energy calculations, it's a little bit more complicated, but it's pretty straightforward. So the first thing we can do with this is look at the slope. So the slope, we said, is the spring constant. Okay, and that's given the symbol little k. So the spring constant is a property of the spring. It does not depend on F, it does not depend on X. The slope is what it is because of the spring that you chose. So if someone else had a stiffer spring, that one was harder to stretch, then we'd see that the graph would look something like that. Okay, there'd still be a linear relationship between F and X, but the slope would be different. Okay, so we call that K. And the units for that, remember, generally are newtons, because that's what you're measuring the force in. And we're dividing it by meters. Okay, it could be centimeters like it was perhaps in the lab. But it's not a newton meter. Newton meter is work or energy. A newton per meter is basically telling you how much force you need per unit distance. Okay, so if you have a spring constant, that's roughly 100 newtons per meter. If you could stretch it a meter, it would take 100 newtons. And that's a nice number to know, because you don't actually have to stretch a string to get the force. If you know K and you determine you want to stretch or compress at a certain distance, you know exactly how much force you're going to have. So that leads us to the idea of, or now we want to turn our attention to, if we're doing force over distance, you're storing energy in it. And if you're storing energy in it, we can calculate that fairly simply. And we saw from the lab that can be found by taking the area under the graph. Okay, so the area in the graph is the work, or the elastic potential energy, okay, PES. And we developed an equation. So I'm just going to summarize the key points from that here. So work, we know, is the area, the force times the distance. So it's going to be 1/2 base times height. The height is the final force, and the base is, of course, how far we stretch it. So note that the work is not just force times distance. If I choose a force right here, and let's say it's 10 newtons, and this distance is, let's say, 0.1 meters, I can't say that the work is 10 times 0.1 because we weren't exerting 10 newtons the entire time. It was started at 0 and it built up to 10. So that's where the 1/2 comes from. Of course, that's equal to 1/2 of the force. If the force is kx, okay, then we can see that if I substitute in there, I got, kx, and we still have the original x. Then we have 1/2 kx times x. Okay, and that's our 1/2 kx squared. So you're going to be asked to find the area or the work done on a spring, and using the graph is really important in the area under the graph. Okay, so Hooke's law from this first one, we have y equals mx plus b. Okay, b is 0 here, so y is force, the slope is k, and x is x in this particular case. Now technically there's a negative in front of there. Okay, let me rewrite that, sorry. Okay, and the negative is important for subtler reasons. It's basically telling you that the force is always in the opposite direction of the displacement. So if I pull it to the right, the force from the spring is trying to pull it back to the left, and vice versa. Okay, so I've already said that the spring constant depends on the property of the spring. We can see that, or it's in the slope. All right, so if we just derive the elastic potential energy equation from above as 1/2 kx squared. Okay, and note that the potential energy goes by the square of the distance you stretch or compress it. So you double the distance you stretch a spring, you get 4 times the energy. When you release it, then conservation of energy kicks in, and you're going to have 4 times the kinetic energy, or whether the spring is propelling something sideways or horizontal or upwards or at any angle. So we want to be aware that if we were to plot PE versus X, we would get a parabolic relationship. And of course, from the lab, if we were to plot PE versus x squared, we would get a straight line. Okay? Now, we didn't talk about this in the lab, but let's add additional one. Let's look at kinetic energy as a function of position. So imagine we have a spring, okay, attached to a wall, let's say, and it's compressed a certain distance from the, or here's the equilibrium position, here's 0, and it's stretched some position x. And then we release it, and the spring is released, and then it's going to be here, back there. So all our kinetic, so we have 0 kinetic when we're at the full x. Okay, so when we're at x, we're at 0. And then when we release it and the x approaches 0 again, we're going to have maximum kinetic energy. Okay, and since kinetic energy goes by potential energy, and it goes by the square of it, we're going to see something that looks like this. Okay, so we're going to see kinetic energy as a function of x, such that the total energy is nothing more than a sum of the green and red line. And so there is total energy. So that's going to be important to look at. We're understanding the energy stored in the spring because usually it's released into kinetic energy. And so we can calculate how fast something is going as a result, or how high. All right, so let's do an example. So we've got a slightly more complicated problem. We've got a spring of K value of 500 newtons per meter. It's compressed a certain distance horizontally. We attach a mass to it, and then we're going to release the mass. And the mass is going to slide forward and then up an incline with the frictionless surface. And the question we want to answer is how fast will it be going at the top? And you are told that this height here is 0.20 meters. Okay, so like any other conservation of energy problem, the easiest way to approach this is by looking at the actual energy transformations. So we start with elastic potential energy. When we converts to kinetic energy right around here, right? It's all KE here, but we're not interested in that. We're interested in what's going on at the top right there. And so what kind of energy does it have? Well, it's still moving, so there's kinetic energy, but it's risen, so there's some potential energy, gravitational. Okay, so now we just use the equation. So we know we're starting with 1/2 kx squared, and that's going to equal 1/2 mv squared plus mgh. And so unlike just falling, we see that the masses don't cancel out, so it does matter. If we were to propel a larger mass, we would not get as much velocity from inertial standpoints. The energy stored in the spring does not depend on the mass. Okay, so we plug in the numbers. I'm not going to do the substitutions here. You should do that. I will give you what each value comes to when you plug them in. You need to verify the self. So the amount of energy stored in there is 2.26 joules based on the information given. That's going to equal 1.47. Excuse me. Wrong part. Okay, that's going to be equal 1/2 mv squared plus 1.47 joules of potential. Okay, so we can see that 1/2 mv squared is going to be the difference between how much energy we started and how much is stored in gravitational potential. So that's going to be 0.79 joules. Hopefully I've done my subtraction correctly. And if we solve for velocity, which isn't too hard here, we see it's going to be going 1.45 meters per second. Okay, so it's a pretty straightforward problem if you understand the energy transformations. Okay, then we can ask how much force was needed to compress it this distance. Okay, since we're talking about force with the spring, the smartest way to approach this is not from an energy standpoint, but from a Hooke's law standpoint, where we know F equals K times X. Okay, so it's very simple. K was given as 500 newtons per meter, again, not newton meters, and this was compressed 0.095 meters. Okay, So if you get your calculator, multiply that out, which I don't have. Oh, I do. Okay, work that out. Okay, hopefully you got 47.5 newtons. Technically, it's negative opposite the displacement of the object. All right, so we'll do some more practice with this and combine it with everything we know, and we'll have a much better picture of how energy transforms with this addition.